We're moving into our first organ system, the integumentary system. So this includes, of course, the layers of skin, the organs of the skin, the hair and nails that develop from within. Let's move along. So we have a more complete list of functions for the integument. So being the superficial covering of our entire body, we have that protective surface. So it's, again, protecting all the 10 deeper systems of our body, and we have various layers of tissues and structures that give this protective feature of the skin. A major way to regulate our body temperature is afforded by the various types of sweat glands. So we'll touch on different populations of sweat glands. And ultimately, as we perspire and produce the sweat, as it evaporates, it removes heat from our body. Deep to our skin, we have our subcutaneous fat for storage of energy, as well as another protective cushion. And these latter two here won't be touched on so much in this lecture, but our sunlight exposure to our skin allows us to create limited levels of vitamin D. Of course, we need that in our diet. And in the next section, we'll see how vitamin D, of course, is important for the skeletal system. As well as in lab, we'll study some of the various touch receptors, the sensory receptors that are embedded in the layers of skin. So starting here with the functions, that's what we see, of course, at the top of this diagram. And our skin has these major components, the cutaneous membrane, which is truly just the two principal layers of skin. Epidermis and dermis are the two sublayers of skin. And then there's further divisions from within. And then the various accessory structures, these are the various organs of the skin. Glands, the nails, the hair follicle structure. So we're going to start on this side, working our way through the layers of the epidermis and dermis, those two layers that truly make the skin. And we can see that here. At the surface, the epidermis, and we'll discuss the multiple subdivisions within the dermis. And then continue here to the deeper layer, and we see there's only two subdivisions to the dermis itself. Once we completely remove the cutaneous membrane, there's a deep underlying layer known as the hypodermis or subcutaneous layer. Truly not considered to be a layer of the skin, but this underlying cushion, and we'll touch on it due to the proximity to our skin. So we'll start at the surface with the epidermis. And by and large, the tissue we find in this area is stratified squamous epithelium. And it's considered to be the keratinized or dry type of stratified squamous epithelium. However, as a whole, there's up to 5 distinct subdivisions of the epidermis. And that's what we're highlighting here. So starting from the very deepest layer, the location of the basement membrane. This again, of course, is epithelial tissue we're discussing at this point. At the very deepest layer, we have what's called, one name for it, the stratum germinativum or stratum basale. And starting from here with the stem cell activity, ultimately over time, cells as they mature get pushed out towards the surface. So we're going to start here at the deepest edge. And again, there's multiple names that can be used here. So right along the basement membrane, just a single layer of cells known as the stratum basale. And of course, with their stem cell activity and their division, producing new cells. And over time, these cells, of course, get pushed out towards now the next few layers. So it's the source of producing the epithelial tissue. as well as a connective tissue cell here, a melanocyte. Of course, melanocytes producing pigmentation, producing melanin, so allowing for that coloration of the tissue. And now this continues into stratum spinosum. So again, the division of these stem cells, they get pushed out into stratum spinosum, and now they begin to specifically differentiate into a cell type known as a keratinocyte. And the keratinocytes, they're now these specialized epithelial cells, and they're the most common type of cell throughout the epidermis. So by far, most of the cells within the epidermis are the keratinocytes. And then we have more of these pigment-producing melanocytes. So we all have this potential for melanin production in the two deepest layers of the epidermis. So now these newly developed keratinocytes again get pushed out to the third layer, the stratum granulosum. And you can see where their namesake comes from. These cells become keratinized, which means these cells get enriched with this keratin protein. Their cell membranes are fortified with additional keratin protein, and this makes the epithelial cells and makes the keratinocytes harder and rigid. They're taking on that strong protective feature that we want. However, as a result, it actually starts to kill the cell. With a strong, rigid cell membrane, they can't undergo as many dynamic processes, and these cells start to die off. And as they're dying off, they thin out and flatten out to truly take on that flat, squamous shape. So now we move from stratum granulosum, and now is where we have some variation here. The stratum lucidum is only in a few areas of the body, and areas that do have stratum lucidum are considered to be thick skin. And those areas include the anterior side of the hand and the inferior side of the feet. So it's only these areas here that have an additional layer to the epidermis, and that's the distinction that makes it thick skin. The fact that it has that stratum lucidum is one major trait of thick skin. So now lastly, at the surface, and this is now everywhere at the skin surface, we have the stratum corneum. So all types of skin, thin or thick, everywhere on the body, has the stratum corneum. And at this point, we have multiple layers, multiple strata of now dead, hard, keratin-rich epithelial cells. So again, that special distinction, they're known now as keratinocytes. Epithelial cells have that trait of cellularity. They're bonded together. So now we have this dead sheet of hard, rigid, protective cells. So this makes a great protective barrier for the surface of our body. This dead tissue could be injured and abraded, but it's protecting the deeper underlying tissues. We already mentioned these cells are enriched with keratin. They're now dry and hard and rigid. And this makes now a nice water-resistant barrier for the surface of our body, so preventing excess fluid loss. So we see that there's these possibility of up to 5 layers of the epidermis. For example, on our face, the epidermis on our face would start with a stratum basale, stratum spinosum, stratum granulosum, and then a stratum corneum, say the epidermis of our face. This would be considered thin skin, whereas thick skin, such as the palm, is now going to have all 5, starting with the deep stratum basale, stratum spinosum, stratum granulosum, the addition of the stratum lucidum, and again, everywhere at the surface, the stratum corneum. So continuing with this concept of now thick and thin skin, another difference seen in the epidermis now of what we consider thick epidermis versus thin epidermis. We already mentioned there's 5 layers to the thick epidermis, and that additional layer, stratum lucidum. The stratum corneum is everywhere at the surface. However, we could use this micrograph as an example. On thick skin, the stratum corneum is much, much more prominent. So there's multiple more layers of keratinocytes for the epidermis of thick skin. And one final trait, the basement membrane, if we follow the appearance of the basement membrane here on thin skin, whereas now that same appearance on thick skin, we can see that the waves and the ridge patterns are much larger and much more prominent. And that trait and shape of the ridge patterns ultimately reflects all the way to the surface of thick skin. And that's what we see as the ridge patterns on the surface of our thick skin. So essentially our fingerprints, palm prints, the treading on the plantar region. It involves now the union of the epidermis and these bulging sections of the epidermis that protrude deeper into the skin. They're known as epidermal ridges. And from the dermis, these bulging areas that protrude out towards the surface is a dermal papilla. So it's that distinct ridge pattern between these two features, which themselves are a genetic trait. That's really the basis for the ridge patterns we have on our thick skin. However, not only is it a genetic trait, the final appearance of our ridge patterns, it's influenced by fetal activity. So movement within the womb, also at that very early developing stage, does play a role in the final appearance of our own unique fingerprints. And every person, despite identical genetics even, will have their own unique, distinct fingerprints. So now moving deep to the epidermis, we have the second layer of the skin, the dermis. So now we have this being made of large amounts of connective tissue. So primarily connective tissues. We'll point out the specific types. We now have a blood supply in contrast to epithelial tissue, which is avascular. We now have the blood supply in this area. And this is where we find the organs of the skin. So the major nerve structures and sensory receptors, glands and hair follicles, they develop within the dermis, and they then, of course, extend out to the surface in some cases. And the dermis itself has just 2 subdivisions. So everywhere throughout the skin, any location, there's just 2 areas, 2 subdivisions of the dermis. So there's the more superficial papillary layer and the deeper reticular layer. So the papillary layer, this is now directly deep to the stratum basale and the basement membrane. And this papillary layer, this is a source of nourishing the living tissues of the epidermis. So the deeper cells that are still living, stratum basale, stratum spinosum, those layers still need nutrients. And that's afforded to by diffusion from the papillary layer. Whereas the deeper majority of the dermis is the reticular layer. And again, being composed of connective tissue, we have this description of dense, irregular connective tissue that's surrounding the majority of the organs of the skin. So most of the organs of the skin are found in the reticular layer specifically. And then we'll expand upon these two. So the papillary layer with its distinct tissue, that loose type of areolar connective tissue, the more superficial area of the dermis is where we're at. And we mentioned how this is what nourishes the living cells of the epidermis. Just an interesting note, tattoo injection has to be inserted deep to our epidermis, and it now becomes this permanent mark that's in our dermis. Whereas now the reticular layer, again, composed of dense, irregular connective tissue. So the strength of the collagen with that woven pattern, that's another strong protective type of tissue. Now, in this case, in the dermal layer of our skin, and the majority of our organs, such as sweat glands and oil glands, develop within this region, and their pores, of course, can lead all the way out to the surface. However, there is a limitation to the strength of collagen, to the resilience of elastic fibers. So, in fact, as we age, our body produces weaker and weaker forms of connective tissue fibers, and that's going to lead ultimately to wrinkling and sagging of the skin. And again, there's a limitation to the strength of fibers, and a stretch mark in our skin is truly just a scar that forms due to damage of the fibers. So it's with these two major layers, epidermis with its possible 4 or 5 subdivisions, the dermis with just 2 subdivisions. This is what makes up our cutaneous membrane, our skin. And before we move on from the skin, taking a look at now a related clinical aspect in terms of, say, surgical procedures. There's what's known as the lines of cleavage. And due to the large-scale arrangement of connective tissue fibers in our dermis, the way that the skin is cut could lead to now various outcomes in terms of healing. So we have this description here, and we have a diagram, just for reference here. If there's an incision that's now running parallel to the lines of cleavage, so if a surgeon needs to go in for some procedure, if they're able to run parallel to these lines of cleavage, the outcome is this incision in the skin, and once it's sutured and heals, it'll heal at a faster rate. And ultimately, over time, it'll have a more aesthetic, pleasing outcome. Whereas an incision that's now at a right angle, if it's going perpendicular, this causes much more damage to the connective tissue fibers, cutting through them. Once sutured, this will be slower and more difficult to heal, and more likely to leave a pronounced scar. And that's really the clinical aspect here. We can think about the difference between a cosmetic surgeon who would want to use this to lead to a better outcome, better recovery, better appearance. Whereas in contrast, you could think of a life-saving procedure where, for example, if a cardiologist needs to get into the pericardial cavity, and a person after heart surgery will be left with a prominent scar on their chest. And that involves this lines of cleavage, the arrangement of the major bundles of connective tissue fibers within the dermis. So now we're in the area of the hypodermis. Again, truly not included as a part of the skin, populated principally by adipose tissue. And here's just one example of how the endocrine system, how hormones, of course, influence where we store our body fat. So there's that typical pattern of body fat storage in men versus women, and that's due to hormonal influence. And adipose tissue, of course, is a protective cushion. It works as a layer of insulation. Those our muscles are giving off heat. The adipose tissue helps us to retain that heat. And of course, storing energy in the form of lipid. So this really functions as a cushion between our dermis and then our deeper bones and muscles. And at that point, we've now worked our way through all of these layers of tissue. There's the strength of the stratified squamous epithelial tissue that's now been keratinized, or considered the dry type of stratified squamous epithelium. There's the large amounts of connective tissue and collagen fibers in the dermis. And here we have the cushion protection of adipose tissue. All right, now we're going into the organs of the skin. So this includes, of course, the hair follicles and the associated structures, the nail structures of the fingers and toes. And we will discuss 5 types of glands. And we notice all of these organs, again, they originate within the dermis of the skin. And of course, many of them protrude all the way through the epidermis to the surface. So we'll start with the hair. And we see that hair has the potential to grow in almost all areas of our skin. So truly, just pointing out the exceptions, thick skin, so the palmar and plantar regions, for example, and areas of the reproductive organs. Those are the few areas that lack any potential to grow hair, typically. Whereas now hair itself forms in these organs known as a hair follicle. And hair follicle, of course, have their genetic traits. There's different shapes of follicles leading to different textures of hair, of course. The pigmentation, of course, is what leads to different colors of hair. And the hair itself, of course, serves a purpose. Each hair strand at the very base is connected to the nervous system. So we have that sensory input, something stimulates a hair, and we have all that additional sensory perception, that touch sensation coming from the hair, and many other sensations, pain, for example. And in some areas, hair gives a protective feature, such as a filter structure for the hair in our nasal cavity or in our ear canal. So taking a look at the hair itself, it's developing in a follicle structure, and follicles can develop distinct and different types of hair. So a single hair follicle has a potential to make different types of hair over time. And we'll discuss here, starting with a very common type known as vellus hair. So vellus hairs, they have just a very short limitation to their growth, very little pigmentation. So you see the description here. It's peach fuzz. And again, potentially this can grow over almost all of the skin surface. If we skip in contrast now to terminal hair, basically the scalp is the perfect example. You also see in this group eyebrows, eyelashes. So especially thinking about the scalp, this hair type has the potential to grow much longer. It can have much more texture and pigmentation to it. And the third group, of course, between these two, the intermediate type. Intermediate hair is especially sensitive to changes in hormones. All types of hair growth, of course, is stimulated by hormones, but intermediate hair is much more sensitive to changes in hormones. And great examples as we age and mature, the growth of pubic hair. And here's an interesting note about facial hair, the fastest growing type of hair. So good example, you can think of a little baby boy. So of course, very early in life, the development of terminal hair on the scalp, eyebrows, eyelashes, fine little varicose cells all around. And as that baby boy ages and matures and testosterone levels rise, decades later, this older man with now pubic hair and facial hair and chest hair and just back hair, again showing that change of hormones and the development of intermediate hair in many areas of the body. But again, due to changes in hormones, a hair follicle can transition from forming terminal hairs at one point on the head, and male pattern balding is an example of when the follicles transition to growing different types of hair or completely losing the function at all. And the hair itself, like the surface of our skin, is now this dead, hardened, keratin enriched, dry type of epithelial tissue. So these keratinocytes. Moving now into the glandular structures of our skin, and we could revisit this description of an exocrine gland. These glands are composed of epithelial cells. The epithelial cells are producing some type of secretion. And in this case, we're going to see there's different types. And regulating our temperature is where we have sweat glands. And we see these two different populations of sweat glands. And then we have now the oil-producing sebaceous glands. And we're going to touch on the typical sebaceous glands, which we see connect to hair follicles. So coating our hair in that protective oil. And sweat glands to regulate our temperature. And we see now related to the structure and development of apocrine sweat gland, we have these two unique examples down here, cerumeous glands and mammary glands. So we'll begin with the sebaceous glands. We see that their location is these are connected to hair follicles. So we're viewing it here. And connected to the hair follicles, that shows their purpose. These glands are producing oil, this sebum within their glandular structure. And this oil is now directly released right into the hair follicle and thus coating the hair itself. And this oil helps to add moisture to the hair to make it softer, and it protects the hair from just being very brittle and breaking. Okay? So we do want some degree of moisture and oil on our hair to protect it from damage and breakage. And a great view seeing how this sebaceous gland leads right into the structure and space of the hair follicle. There's now the different types of sweat glands. So there's the apocrine sweat glands. And then we see here merocrine, or also known as eccrine. It could be said either way. Merocrine sweat glands or eccrine sweat glands. These are now the very widespread type of sweat glands across the body. And we can see their structure. They are smaller in size, and their pores lead directly to the surface of the epidermis. Whereas the more limited type, the apocrine sweat glands, we see they are larger in size, but their pores lead first into a hair follicle, and in turn the hair follicle leads to the surface. And we see the few areas that have this, well, these areas are all areas that produce or can produce hair. So we see the axilla, the underarm, the areola, so that skin surrounding the area of the nipple, as well as the groin, the inguine regions. These all have the potential, the possibility for hair growth, and that's the few areas that contain apocrine sweat glands. But of course, what both of these have in common is they respond to temperature. If we're exercising our muscles are giving off heat, and due to that increase in temperature, we have the response to activate sweat glands, and we perspire, and we're able to cool off as it now evaporates. Mammary glands, of course, developed further in women for the production of breast milk and breastfeeding and in nourishing a young baby. And cerumeous glands, cerumen is the term for earwax. And this is another protective feature. So the skin in our ear canal has this production of cerumen, and this waxy substance is in place to try to trap any particulate matter, any debris, and have it get trapped into the wax as opposed to penetrating deep down into our eardrum. So both the hair that's in our ear canal and the wax are both providing this protective feature. So now moving on to the mechanism of how these glands work. We touched on this in the epithelial section, so you may want to review right back to this portion. We described the three mechanisms of secretion: the bursting process of holocrine, the numerous secretory vesicles used in the merocrine process, and detaching the superficial tip of the cell and the apocrine process. And now we're just matching this to distinct glands of the skin, the 5 that we just covered. So we notice those oil-producing sebaceous glands. Their cells produce large amounts of sebum to the point where the cells swell up and burst. And that's how the sebaceous glands release oil into the hair follicle, by rupturing the cells. We see that both types of sweat glands, apocrine and merocrine sweat glands, both types of sweat glands use the multiple secretory vesicles known as a merocrine process. And then lastly, in the release of breast milk from the mammary glands, in this case, the development of breast milk first accumulates in the superficial tip of the epithelial cells, and then that superficial tip detaches, and that is the apocrine mode of secretion. So we don't want the names to confuse us. There's the names for the processes, and there happens to be a merocrine process and an apocrine process. But we don't want to get confused by the names of the glands: merocrine sweat glands, apocrine sweat glands. And you see that the name of the gland does not always match up to the name of the process. So now lastly, the nail structures, and the theme for this system is protection, right? That's what the integument system affords for our body. And having the hard, rigid finger and toenail structures are giving us increased protections at the distal tips of our extremities. That's the major takeaway right there. We do have these lab terms that we'll bring up called the hyponychium. This is now just simply the skin that's running under the distal end of the nail, or the eponychium. We see the skin running over the proximal exposed portion of the nail there. So of course, the surface of our skin just kneading up and connecting with the nail structure itself. And the natural color that we see, of course, is afforded by the blood supply that's just seen deep to the nail structure itself. So to put things together now, we went through the layers of tissue, the types of cells. We discussed some of the organs within the skin. So this is just putting things together now to finish up this chapter. So starting at the surface, The first principal layer of the skin, epidermis, largely made of stratified squamous epithelial tissue, and it could be called keratinized or dry. So the dry or keratin-rich type of stratified squamous epithelium. There's a possibility of having 5 layers. So again, the stratum corneum's everywhere at the surface. It's enlarged and more prominent on thick skin. Another trait of thick skin, that's the only area that has the stratum lucidum. Stratum granulosum, of course, found all throughout the skin. And this is that process of keratinization begins. And another unique trait of it is, one trait of African ancestry is, despite the fact that melanocytes, the pigment producing cells, are only located in the 2 deepest layers, with increased production of melanin, some of this melanin can transfer into the 3rd layer. And that gives a darker skin color and increased UV protection from the sun. However, there's no melanocytes in the stratum granulosum. Those are only limited to the 2 deeper layers. Deep to that, there's the stratum spinosum. And then ultimately, the deepest layer right along the basement membrane, stratum basale. And again, this is where the stem cell activity is occurring, and one of the 2 layers that contain the melanocyte cells. So beyond the entire epidermis, deep to that, we reach the dermis, that just has 2 partitions to it. There's the papillary layer produced from areolar connective tissue. We do see some of the superficial nerve endings. So what's known as a Meissner's corpuscle. Being so close to the surface of the dermis, these can respond to a very delicate and light touch, and thus we perceive it as a very delicate, soft touch when they are stimulated. Deeper to that, the majority of the dermis is the reticular layer, composed of dense, irregular connective tissue. So all of that strength of the woven collagen fibers. And it's in this areas where we find the majority of the organs of the skin. So for example, those oil-producing sebaceous glands, the 2 types of sweat glands. And just an interesting note here is that our unique odor comes from the apocrine sweat glands specifically. Beyond the area of the dermis, now beyond the area of the skin, we have the underlying subcutaneous fat. So the cushion of the hypodermis, composed largely of adipose tissue. And here we notice another type of nerve ending known as a Pacinian corpuscle. And since these are so deep in, beyond the skin, located within the adipose tissue, it takes a much stronger level of force and pressure to stimulate these, and we interpret their activity as a much stronger, deeper pressure or a much stronger, forceful touch sensation. So at this point, we've now worked our way through this chapter and thus this image. And we started with the major layers of the epidermis and its subdivisions. On this figure here, the fact that we see hair, this must be thin skin. Thick skin does not develop hair. So this would have just the 4 distinct strata to the epidermis. We get into the papillary layer and we can start to see the blood supply. And again, it's diffusion from the papillary layer is how we nourish the deep living cells of the epidermis. We can see that Meissner's corpuscle, or another name for it, tactile corpuscles found in this papillary layer. The deeper majority of the dermis is known as the reticular layer, and this is where we find the majority of the skin's organs. And then finally, the subcutaneous or hypodermis, made principally composed of the cushiony adipose tissue.